Okay. I guess there's two announcements. First of all, go to pi minus 0.01 day. And then when you're done, come back here. So we have Felipe Rincon from UC Berkeley who's going to give a wonderful talk in our, I think it's going to be wonderful. Is it? He's going to talk in the Algebra Geometry Combinatorics seminar, so you should come back for that. And we'll see if he lets me film, and then the people in Colombia can see it also. Okay, so I taught you a little bit about topology. I taught you a little bit about homology groups. Now, there is only one more thing that I want to say about homology groups, which is that generally people call them homology groups. And the way that I have defined them, they were vector spaces. Right? So you might be a little bit confused by this. And so just to give you an idea of why that is, the reason is that we define these Ci of delta to be the vector spaces generated by the I-dimensional faces. Right? So we were kind of considering combinations of faces with coefficients in a field. But we can do the same thing with coefficients in an abelian group. So for example, I mean, we defined Ci of delta to be field to the faces of delta, but we could have defined it to, instead of having a field here, we could define this to be the integers or any other abelian group. Okay? And then we can develop the whole theory again, but now instead of having vector spaces, we're going to have abelian groups. Okay? So then we will make Ci of delta an abelian group, then these Bi and Zi are going to be abelian. You can compute the homology, but now the homology is going to be not a quotient vector space, but a quotient group. And in that case, instead of getting homology vector spaces like we're getting here, you're going to get homology groups. Why would you want to do this if it complicates things? Well, the reason is that depending on what you put here, whether it's a field or a particular abelian group, this might or might not be able to tell some topological features. So for example, you guys might be familiar with the Klein bottle. And if you are not, maybe you should Google it so you can see what I mean, because I can't draw a good picture for this. But the Klein bottle is this surface that you can't, it's a bottle that you can't really put water into because it has no inside and outside. Okay? And this is something that you can detect with the homology, but you cannot detect it if you use a field. You need to use an appropriate abelian group to see that. And so there are advantages to using things other than fields, and this is what you will do when you take algebraic topology. But you might have noticed that I slipped and called things homology groups. Well, they basically are homology groups also. Okay, so that's just the end of my general discussion on algebraic topology. And what I want to do is come back now to algebra and make something very precise, because we kind of have the feeling that the computations that we did for free resolutions look very similar to the computations that we did for homology. And what I want to do today is make that very precise. Okay? So here's an example. This is the example that we have talked about several times. So we have a simplicial complex delta. It looks like this, with a hollow tetrahedron and then a triangle and an edge. Okay? And then we consider the Stanley-Reasoner ring, which is the quotient of the polynomial ring, by the ideal generated by the minimal non-faces. The minimal non-faces are the tetrahedron, which is empty, so A, B, C, D. Then this empty triangle A, B, E, and the empty triangle A, C, E, and then the edge from B, D to E. Okay, those are the minimal non-faces. Those generate the Stanley-Reasoner ideal, and the quotient is the Stanley-Reasoner ring. Okay? And we have developed techniques so that we know how to write out a free resolution for this, guy, right? By the way, you guys now realize that these are not things that you want to do in hand if you can help it, especially if the example is big. So there is software that you just ask it to give you a free resolution, and it will. Okay? And if you were to do that for this guy, then this might be what you get. Okay? This is an example of a minimal free resolution of this guy. So maybe I'll call this like this. It's a minimal free resolution. Okay. And so how is it that this thing looks like a homology computation? What do I mean when I say that? Well, the setup is the following. Let's say that consider a minimal free resolution of a monomial ideal like the one that we have here. So that looks like this. You might want to do this for the ideal, or you might want to do this for the quotient. So either way is fine. So that's an example for the quotient. Let's do here for the ideal. We saw that monomial ideals are homogeneous, right? And that means that actually we can make this be a graded resolution. Okay. And remember that the way that goes, for example here, is that we want all the maps to take things of degree I to things of degree I. And the way we do that is that we kind of cheat a little bit and change the grading on all of these guys. So for example, when we have the map here from R to the fourth to R, well, the way that I have written it here, it's not degree preserving, right? Because an entry here is a matrix with a column vector with 4 entries. And for example, if I take 1, 0, 0, 0, that goes to DE over here. And I don't want to change degree, so the way that I do that is that I shift the degree in the first coordinate by DE. Then I shift the second coordinate by ABE, the third by ACE, the fourth by ABCD. And so what we get here is this version of R to the fourth where we have shifts allowed. So if I want to include a grading here, then if there is no grading, then this is just R to the something, right? But if I do have a grading, then I have some shifts, and the way that I decided to write this was like this. So basically, each one of my copies of R is going to have a shift of some vector minus A, and then I just say how many times that guy appears, and I call that beta sub I comma A. Okay, and I do this over all exponents A over the naturals, but of course most of these guys are going to be 0. Right? Most of these Betti numbers are going to be 0, and this might look like, for example, the way it would look over here is that the graded version of this guy we said was R of DE, which now looks like 00011, plus R of ABE, which looks like 11001. ACE, we get this, and ABCD looks like this. Okay. So in this case, these are really the only 4 values of A that contribute, and each one of the Betti numbers is equal to 1 because there is no repetition here. Okay. All of these guys have different shifts. So I call this number beta sub I of A to be the ith Betti number in degree A. And you will remember that one thing that I mentioned about this is that the fact that you have a minimal free resolution, we said that basically there is a unique minimal free resolution up to isomorphism. And what that means is that if this guy is minimal, then all of these FIs are going to be the same. You're going to get exactly the same Betti numbers. And so the Betti numbers only depend on the ideal. They don't really depend on anything else. Okay, so these are really just functions of I. Okay? So the point is that basically, if we can compute these numbers, then that gives you a lot of information about the ideal. For example, we saw how you can get the Hilbert series immediately as soon as you have these numbers. So if you can compute the Betti numbers, that gives you a lot of information about your ideal. For example, the Hilbert series, which is one of the things that we really like to compute in this class. For example, the finely graded Hilbert series. And of course, if you have the fine one, you have the coarse one. Okay. Yeah, question? The question is, have we computed any free resolutions that are not minimal? I don't think so, actually. I don't think we have seen one in this class. Now, how can I make one? Well, I could, for example, I don't know. I mean, I could just add garbage to this one. You know, I could, for example, add another copy of the ring here, and then map to 0. I mean, and then don't map to that guy. You know, I could put, for example, a 5 here, but then have this guy only map to the first 4 coordinates, and have the 5th coordinate map to 0 here. So that means that really that 5th guy is not really there, but basically that's the extent to which resolutions are not free, is if you take this one and you add garbage to it. And there is that precise statement basically that any resolution is the free resolution plus a resolution of 0, which is basically just doing a lot of work to get 0. Okay. So in practice, in practice, all the ones that we have seen are minimal, I think. Okay. So, of course, this is the big if, and the point of the class today is that you can compute this guy, and you can compute it topologically / combinatorial, which is good news because we saw that even though we know how to compute free resolutions, it's kind of a hassle. And I don't know about you guys, but I prefer to look for holes in simplicial complexes. And basically, what I'm going to show you today is that we can do this. Okay? So how am I going to show this? Well, I need to make another definition. So definition, given a monomial ideal I, and a vector b in n to the n, I'm going to define a simplicial complex, which is called the upper Koszul simplicial complex. Of I in degree b is given by this, so I denote it like this, Koszul in degree b of I, and this consists of the square free tau such that x to the b minus tau is in the ideal. Okay? So let's see an example of what this looks like. So let's do it for this ideal and for this b. So what does this guy look like? Basically what I'm looking at is I want to take my vector b and I want to subtract things from it so that I land in the ideal. Okay? So we know that this basically corresponds to the monomial a, b, d, e. And maybe the first question is, does a, b, d, e live in this ideal? And it does live in the ideal, right? Actually, let me write the ideal again because the camera is not showing it right now. So the ideal is a, b, c, d, a, b, e. Is that a c? A, c, e. It takes some imagination to see that that's a c. Anyway. So we need to figure out what we need to take away variables from here and land in the ideal. Okay? So the first question is this guy in the ideal? And it is, right? Because this guy is a multiple of a, b, e. So if we take nothing away, then we're in the ideal. Now, what can I take away? What single variables can I take away and stay in the ideal? Well, if I take a away, then b, d, e is in the ideal. It's a multiple of d. If I take b away, then a, d, e is in the ideal. If I take d away, then a, b, e is in the ideal. If I take e away, then a, b, d is not here. So it doesn't get to be, it doesn't get to live here. Okay? So those are the single guys. What about the pairs? I need to take off two variables so that I land in the ideal. Now, the thing is that I have something of degree 4. So if I take two variables, I'm going to be of degree 2. And there's only one guy of degree 2 here, which is dE. So the only possible thing I could do is take out a and b. So this is what my simplicial complex looks like here. Okay? So it's just this guy. Okay? An easy check that you should do, and we'll put it on the forum, is that this really is a simplicial complex. So this gives you a recipe to get a simplicial complex from I and B, and then our next major theorem that we're going to prove is the following: that if you want to know the Betti number, the ith Betti number in degree B of the ideal, then all you have to do is compute the I minus first homology of this guy. So you compute the reduced homology of this guy, I minus 1. Now, what am I going to get here? I'm going to get some vector space f to the something, and then the dimension of that vector space is going to be what you want. So the dimension of an f vector space of this guy is your Betti number. Okay? I don't know about you, but I think this is a pretty cool theorem, because it basically tells you that this is the algebraic invariant that we want to compute, and it just tells you, just draw the simplicial complex, look for I minus one dimensional holes, and that's the number. Okay. By the way, so this is if you wanted to do it for I, but if you wanted to do it for R mod I, like we did over there, then basically this is the same thing as the I plus first Betti number of R mod I. So, for example, what does that tell us in this example? B equals 1, 1, 0, 1, 1. Okay. For example, we have a zero homology here, right? Because we said that the zero homology can tell these ways of separating your simplicial complex into two. Okay. And we have one of those things because we said that the whole BD is the same as the whole AD. Okay. So we can just look at this picture and we'll know that we have an f to the 1 here. And so that means that the 1 here should be the Betti number of, I guess I is 1 here, so we get beta 2 comma B of R mod I. Right? I minus 1 is 0, so I plus 1 is 2 in R mod I. Right? So because I have a hole here, that tells me that if I go to the second level of my free resolution, I should see one term of degree 1, 1, 0, 1, 1. So let's look for it. This is the guy we're resolving. This is F0. This is F1. This is F2. And so it's telling us that over here, we should be seeing that one of these guys gets shifted by that degree 1, 1, 0, 1, 1. Okay? And if you look at that, that's going to be the first guy. So, now the second guy. If you look at the way that this guy gets, the second generator goes to here, right? And this guy has degree AB shifted by DE, and degree D shifted by ABE. So that means that the second term over here gets shifted by ABDE. By the way, I'm going to show you either at the end of today or at the beginning of tomorrow an easier way to spot this stuff. So that, but if you do it carefully, you'll see that this guy looks like minus 1, 1, 1, 0, 1, minus 1, 1, 0, 1, 1. Sorry, 1. 0, 1, 1, 1, and let me just write all the shifts for you so that you have them all in one place. But right, so the point is that the reason why this guy lives in this dimension is because of this homology and this simplicial complex. Okay. So that's our next theorem that we're going to spend a little while proving. So is it clear what the theorem is saying? Any questions about it? This is a very good point to ask questions because I'm going to spend maybe at least another hour proving this. So.
Is this something between y and beta ib and beta I plus, or y is like the beta number for I?
Oh no, I haven't given you even a clue of a proof. So you're not supposed to know why this is true. And well, there is a simple reason why this is true, which I didn't tell you, which is that, well, I'll tell you when I prove the theorem. But basically, the resolutions of this guy and the resolutions of this guy just differ by putting or not putting an R. Basically, what I want to say is that if this is a resolution of R mod I, then this is a resolution of I. And that's the reason why. That's the reason for that. But yeah, I'll say that more carefully when we get to it. Any other questions about this statement? Yeah?
Now, I can't figure out what a Betti number is. Like, is that power in that the sort of dimension in the three resolution chapters?
Yeah, so the question is what are the Betti numbers? Maybe you're asking me to reconcile that definition with this example for you. So where do you see the Betti numbers here? Well, basically the Betti numbers are the exponents of these guys, which in this case every exponent is either 0 or 1 because all the shifts are different. Okay? So for example, what I'm saying is that the number of times that I have a shift of 1, 1, 0, 1, 1 in level 2 is the number Betti 2, 1, 1, 0, 1, 1. For example, the fact that I have a term here means that this guy gets to be A in that definition. And the exponent, which again is 1 because I only have one appearance of this guy, is beta sub step 1 of the resolution and 1, 1, 1, 1, 0. Okay? So the Betti numbers are just kind of you might call it an economical or a very not economical way of storing this stuff. I'm just saying for every vector like this, I'm telling you how many times it appears in each level. 1, 1, 1, 1, 0 appears, it doesn't appear here, it appears once here, 0 times here, 0 times here. So those are the Betti numbers of level I for this A. So the reason I call it more economical is that it looks very short there. The reason I call it less economical is that basically I'm defining an infinite sequence where almost everything is 0. So the Betti numbers are just storing all these shifts, basically. All right. So we need to do a little bit of theory to get to the point where we can prove this theorem. And we have to review a construction, which is the construction of tensor products. This is something that you probably saw briefly in your previous algebra class, and I will review for you now. So, tensor products. So if you have two R modules, let's call them N and N. Then I have a tensor product which is denoted like this, M tensor product N, and I've put an R here to signify that this is an R module. We were doing this over R. The tensor product like this is the following thing. So it's an R module. And how do I define the R module? Well, we saw that one way of defining a module is by giving generators and giving relations. So that's what I'm going to do. So first I'll tell you what the generators are. So this is the free module generated by just kind of formal ways of taking an element of the first guy and an element of the second guy. Okay. So what this tells you is that you can think of an element of the tensor product as a combination of symbols like this. So these are the generators, and now I have to tell you what the relations are. And the relations are basically telling you what are you allowed to do with tensor products. So one thing that you're allowed to do is that, so these are going to be all the relations. So if you have something like this, sorry. Let's say that you have something like this. So this is going to be an element of my tensor product. And this is supposed to be linear in the sense that this should be equal to this plus this. Okay. So that means that if the right-hand side is fixed, then you can distribute the left-hand side. And the same for the other side. So if the left-hand side is fixed, then I can distribute the right-hand side. Okay. So far, I'm only telling you kind of additive relations between that live in here. But then I also need to tell you how, because this is an R module, I need to tell you how to multiply something here by a ring element. Okay? And then basically the rule for that is that if you, I mean, the point is this, that you need to define this, right? You need to define ring element times element here cross element here. Okay? But there are two sensible ways to do this. You could multiply R by M, because M is an R module. Or it's also sensible to multiply R by N, because N is an R module. And then you should basically get the same answer either way. Okay? So Rm cross N, tensor N should be the same thing as M tensor Rn. Okay, so this is for M and M prime in M, and an M prime in N, and R in R. Okay. So this is the tensor product of two modules. It's a module.
Is there a reason why you can't distribute the R to both of them? That the other chips thing?
So your question is, why not define this to be Rm tensor Rn? Well, that would be a different definition. But over here, this is what R squared does to Mn. Right?
Right.
Because you could take an R out, and then you could take the other R out. So I don't know if some of you guys are familiar with the categorical point of view. Then basically the thing is that you want this tensor product to be kind of the most general thing that factors through bilinear maps. If that means something to you, great. If it doesn't, then maybe we shouldn't dwell on it too much. But that is the reason why this is the definition that one wants. Okay, so let's do some examples of this, just to get a feel for how these things work. So for example, what's this? The tensor product of the ring with the module. Okay, so here M is an R module, and I want to define this. Now, you might have the intuition, and it's a sensible intuition, that you're making a bigger thing, right? You're kind of taking two modules and multiplying them into something bigger. But that intuition is actually a little bit off, as you will see here, because what I want to show you is that when you tensor by, I guess it's debatable whether that intuition is off, but the point is that when you tensor R and M, you're just going to get M back. So why is that? Why is that?
So I feel like intuitively, since M is an R module, right, when you create this tensor product with the ring that it's over, you just get itself. And that's just very intuitive.
Yeah, I mean, so that's why I was saying that the point is that this is a very special R module in that it, in a way it's kind of the unit as in this sense. Okay, when you take the tensor with R, you get the same thing back. How do I prove this? Well, I need to exhibit an isomorphism. Okay, and this might be puzzling because, again, the point is that you might think that this is bigger than this, but what does a generator here look like? Well, we said that a generator looks like this, right? This is in the left-hand side. And somehow I want to get out of this a single element of M. Okay? Well, what I can do is the following. I can say that R is equal to R times 1. Right? Because this is operation in the ring. In the ring, R is equal to R times 1. And now I can distribute R over to the other side. And now the way that I'm supposed to interpret this is that I take my modular element and I multiply it by the ring element. Okay. So basically what I did is that I showed that any element in the left-hand side, you can kind of think of it as an element of the right-hand side by just putting a 1 in the first coordinate, and it's just Rm. Okay. And so if you send this to Rm, you can easily see that that's an isomorphism. What if M is a graded R module? Well, remember that if M is graded, then R has to be graded, right? Then what happens when you look at this guy? Your ring, where you shift the grading by A, where A might be a number, it might be a vector, and you tensor that with module. Okay. Well, basically you make the same computation, and you see that you get the module back, except that here you're thinking that this guy lives, that the one lives in degree A here. We're shifting the degree by A, and that's going to come through here and also shift the degree of M by A. And so we get an isomorphism like this. Okay. So these are just a couple of examples. And a concrete example, which is the one that we're going to use the most, so this is the example we like the most. What happens when we take this guy, we shift it by a vector A, and we take the tensor product with our field? Well, basically, according to this, we just get the field shifted by A. So we get just a copy of the field that lives in degree A. how are you supposed to think about this? Well, this is supposed to be a tensor product of modules, right? So you're supposed to think of this as an R module and this is an R module. So it's clear how to multiply something here by a ring element. How do you think of the field as an R module? If you want to think of the field as an R module, you want to take a field element and teach me how to multiply a field element times any polynomial and get a field element back. So F is an R module. How? Take an element of my field, and now you're supposed to multiply it by some polynomial that maybe we call Pfx1 up to xn. It's a polynomial. How do I get a field element out of this? I mean, the regular multiplication gives you a polynomial. You don't want a polynomial. So the way that you do this is that you throw out all the higher order terms and just keep the constant. And that's the same thing as evaluating at 0, right? Because all the higher order terms have variables send you to 0. So this is just by definition. You take this, you multiply it by f, and you put x equals 0. Okay. So that's my very quick definition of tensor products. And I think I can erase this. I'm not going to get back to this today. So now let me think of a different setup. Let's say that we have two R modules like this. Okay. And now let's say that we resolve one of them, M. Okay. So let's say that we have a free resolution of M. It looks like this. Okay. So this is a chain complex which is exact at every step. Okay. What I want to do is that I want to take this whole thing and tensor everything by n. Okay. So I'm going to tensor everything by n. And if I call this guy f little dot, then I'm going to call this guy f little dot tensor n. Okay. So what I mean by this, well, first of all, the things that you see here are just all of these guys tensored by n. You can convince yourself that 0 tensor n is 0. So far I have defined for you how to take each element here and send it to an element here by this tensor product. But I haven't shown you how to take the maps here to define maps here, right? By drawing this, I'm already saying a lot of things. I'm already saying that I know how to map this to this. So how am I supposed to do this? Well, what I'm going to do is I know how to map fi to fi minus 1. So I do that using the coordinate delta I on my first coordinate. And then on my right coordinate, I just use the identity map. Okay. So in other words, what I do is to map here to here, I just need to tell you where to map the generators. Okay. And if I have a generator like this, I'm just going to map it to, well, this guy lives in I, so I know how to map it into here. And I just leave the other side alone. Okay. So now I have maps. Now, if you think about it, what happens if I mean, the next thing I want to claim is that this is a chain complex. And what I mean by that, remember, is that when you take two of these maps and take their composition, you get 0. Okay? I know that here, if I map delta I minus 1, I get 0. Why is that true here also? Well, think about doing this twice. Right? You're mapping fi tensor n to fi minus 1 tensor n to fi minus 2 tensor n. And what you're doing is you're leaving the right side, you're leaving the n alone at all three steps. And here you're going f, then delta if, and then delta I minus 1 delta if, which is 0. So what you get is 0 tensor n, which is 0. So this is a chain complex. Okay? And once you have a chain complex, the natural question to ask is it exact? And it turns out that it's not necessarily. Okay? So this guy was exact by definition, but you might have lost that property here. You probably did. Okay? And so, since it's not exact, then we want to measure to what extent is it not exact. And that's what homology does for us, right? Homology tells us at each step how non-exact this is. Okay? So it's a chain complex, but it's not necessarily exact. So to measure the non-exactness, I take the ith homology group of this thing. Okay. That measures how not exact this is, and I'm going to call this Tor sub I super R of n comma n. This is the definition of this thing. So again, what is this? It's basically when you take a free resolution of M, which is exact, and you tensor it by n, you lose exactness. And this Tor guy measures how much exactness you lost. Okay. That's the definition of Tor. Okay. Now, there's two very nice facts about Tor that should be surprising to you if you haven't seen this before. So here's two important facts. So the first fact is something that is inherent in the notation. You see that I call this Tor I, R, and M. Okay, that's a lot of symbols. And what those symbols say is that the answer depends on I, the answer depends on R, the answer depends on N, the answer depends on M. But there's a very important symbol that you're not seeing anywhere there, which is F, and we used F to build everything. Okay? And it's a nice fact that this doesn't depend on F. So we could have chosen any free resolution, and we would have gotten the same guy. So Tor, I, R, and M doesn't depend on the free resolution that we chose. I think that makes this definition more interesting and more worthwhile to study if it's really independent of your resolution. So that's the first fact. And then the other fact is that the Tor of n and m is equal to the Tor of m and n. Well, not equal, but isomorphic. So if you think about it, this is amazing, because these two things mean very different. These two objects, by definition, are very different. For this guy, you take a free resolution of m, and you tensor it by n, and you see how much you lost in the exactness. And for this one, you do the opposite. You take a free resolution of n, you tensor that by m, and you see how much exactness you lost And the fact is that you get the same answer no matter which way you do it. It's a really nice fact. And the nicest thing about it is that it's true. So these are two very important facts. And maybe I have one last fact that I can squeeze in. Let's see, this is a race against the camera, against the self-timer. So if M is an n to the n graded R module, then the Betti number beta I b I is equal to the dimension of the Tor of I when you tensor it by your field and you take the Betti component. Now this is a lot of symbols, and when you're done parsing what the symbols mean, you'll see that actually the statement is not a very difficult one. This is almost true by definition. The thing is that there's a lot of definitions here. But so our plan for proving this theorem is that first I'm going to